Okay, Assalamualaikum and a very good day to all. So we are going to discuss the next chapter, which is uniform circular motion. Okay, so we are going to discuss the applications of uniform circular motion in conical pendulum and also banked and unbanked track. But before we go with that, we are going to find the directions and the magnitude of the uniform circular motion equations and also relate it with the centripetal force. Okay, let's start now. Okay, so basically when it comes to accelerations, we know that the acceleration is basically comes from rate of change of velocity of velocity. Okay, which means that if we have a change in terms of magnitude of velocity, then you are going to have an acceleration. So it means that when you have a constant speed or constant velocity, we know that the acceleration is going to be 0. But there's a conditions where even though you have a constant speed, you still have an acceleration. How come? Okay, it is because of change of direction. Okay, let me show you the example how the change of direction can actually produce an acceleration. Okay, example, if we have one car moving with the initial velocity of 5 meters per second to the right, and then is continuously moving to the right with the 5 meters per second also to the right. So what happens is when we put it inside the formula, we know that the formula for average acceleration is v final minus v initial t final minus t initial. So at v final is going to be 5 meters per second to the right, and it's going to be minus with the 5 meters per second also to the right. So the t at initial minus t final, then you are going to get 0. Okay, but this is in the same direction. What if we change the direction? Okay, so when we change the direction, what happened is, okay, so example, you have one car moving in the same direction, moving to the right 5 meters per second, and we denoted this as a v initial. Okay, and then suddenly and then the car continuously moving with the same velocity 5 meters per second, but it's going to the left. It's changed the directions. So when we put it inside our calculations, what happened is v final minus v initial, t final minus t initial. So what happened is the final going to be -5 because it's moving to the left. So and then the initial going to be 5 moving to the right. So you are going to get -10 over time. Okay, so means that we can actually prove that it's not only the change of velocity, the change of magnitude can produce an acceleration. The change of direction also can produce acceleration. Okay, yes, okay. So this one, we are going to use this concept in uniform circular motion. Okay, so when it comes to the uniform circular motion, the things that you need to understand here is the velocity always be constant, but the directions of velocity continuously changing, because you can see that it's moving to this one, and we put it here is going to move it to these directions, is going to move in this direction. So basically what happened is it move with the same velocity, but it always change direction, therefore is going to produce an acceleration. But what is the direction of this acceleration, and what is the magnitude of this acceleration? Okay, example, if you have one circle, okay, you have one circle, okay, and this circle and it means that you have a circle with the velocity is continuously changing the direction, and you need to take note that the velocity always be tangential to the circle. Okay, example, if we have this one, we call as the radius one, and it's produced the velocity of v1 or initial. Okay, and then it's moving, okay, from r1 to r2 is moving with some theta, or we can call it as angular displacement. and then the velocity here, always tangential to the circle, is going to be v2. So what happened here is, when it's moving from A to B, the angle here is basically the same as angle here. Okay, so now we are going to find the directions of acceleration first. Okay, so I'm going to take this one and then put it like this as a v1. Okay, and then I'm going to take this one and put it like this. Okay, so this I'm going to denote it as a v2. Okay, so you know that the change of velocity is basically v final minus v initial. So when I rearrange these equations, I'm going to get the v2 will be the change of v plus v1. Okay, so what happened here is, we already learned about the tail to tip method. So you can actually assume that the v2 is basically the resultant. So for you to decide the directions of the change of v is going to be in this direction, because from tail to tip, and then from tail to tip, and then you got this one, which is as the resultant. And that's the reason why you can actually see that this one we can denote it as a change of v, which means that this part is toward center. Okay, and that's the reason why when you have a object moving in circular motion, the centripetal force, or we can call as a radial acceleration, going to be towards center. Okay, it can be centripetal acceleration or it can be radial acceleration, because from this one. Okay, so we already found the directions of centripetal acceleration, which is toward the center. What about the magnitude of the centripetal acceleration? Okay, so what happened here is, as you can see that this angle, this one and this one have the same angle, so we can actually put that as a theta. You can put it as a theta 1 equals to theta 2. So I'm going to put this as theta 1 and I'm going to put it as a theta 2. Okay, so if as example I transfer this picture, I'm going to get like this. This is theta 2. Okay, and then the theta 2 is basically r1 and r2, and this one, because okay, you have an arc length here, but when the t approaching 0, the r2 and r1 we can actually say that is almost parallel. So we can actually see that the arc length equals to the chord length. The arc length will be equals to the chord length if the theta approaching 0, or we can actually say that the theta is very, very small. Okay, so I can actually put it as a change of L over there, because it's moving from A to B. So basically they have some change in terms of position. Okay, and then I'm going to put the same picture here with the V. Okay, so I have the V1 here, I have the V2 here. So basically what happened is, as a t approaching 0, or we can actually say that the t is very, very small, so this one we can actually put it as a change of V, which is come from this one. Okay, so because the angle for both is basically the same, so because the angle for the both is basically the same thing, so we are going to use this statement, theta 1 equals to theta 2. Please remember the formula for the theta, which is the theta, which the angle is equals to the L divided by R. Okay, so here, okay, just recall everything back. So like example for this angle theta, this is going to be L and this is R. So you're going to get this formula. Okay, so now we are going to use this concept, which is theta 1 equals to theta 2. Okay, so theta 1 going to be this one, and as a as a t approaching 0, or we can actually say that the t very, very small. So what happens is your L here going to be your change of V. Okay, and then your R here going to be V1 or V2, because as I mentioned before, if t approaching 0, we can actually say that the t very, very small. So what happens is V1 and V2 basically parallel to each other. Okay, so this one you're going to get V. Okay, and theta 2, the L here going to be the change of L. Okay, and then your R here going to be R1, because when your t approaching 0 or t very, very small, what happens is your R1 and R2 will be the same. So I'm going to put it as a R only. Okay, so rearrange the equations, then you are going to get V change of V equals to V over R change of L. Okay, so as a t approaching 0, we know that is going to call as an instantaneous acceleration. Okay, instantaneous acceleration. So what happens is you are going to have the formula as limit t approaching 0. You are going to have a formula of rate of change of velocity. Okay, so it means that now you are going to put your change of V here into this formula. So you are going to get what? You are going to get V over R and change of L divided by the change of T. Okay, so this one basically represent what? Yes, very good. It's going to represent velocity. So you are going to get your centripetal acceleration, okay, which is the formula going to be V square over R. Okay, and that is the formula for centripetal acceleration, or you can actually denote it as a AR, which is radial acceleration. Okay, so now it's already proved that the directions for the centripetal or radial acceleration is going to be toward the center, and the magnitude of the centripetal acceleration is going to be V square over R. Okay, so before this, when it comes to the acceleration, the V and the R and the A always be in the same direction. Okay, however, for this one, your V and your A basically perpendicular to each other, because V is tangential to the circle and acceleration is toward the center. Okay, because when you have a rate of change of velocity, because the acceleration is going to follow the rate of change of velocity. Okay, so if the rate of change of velocity is toward the center, definitely your acceleration is going to be toward the center. Okay, understand? Okay, let's move to the next part. Okay, so I already show you how to derive the equations. Okay, so we can call it as centripetal acceleration or radial acceleration. So centripetal means that center, that pointing acceleration. Okay, so this is basically the things that I already showed you before. Okay, you can actually refer to this. This is the proper picture of it. And then I already explained here also. Okay, and then this one is basically the one that I already showed you, how to find the magnitude of centripetal acceleration. Okay, and then please take note the formula going to be centripetal acceleration equals to a V square over R. So when it comes to the uniform circular motion, which means that the object moving in a circle, definitely you need to relate with the frequency and the period. Okay, so please take note the frequency is basically the number of revolution per second, which is sometimes we can actually put the unit as a revolution per second, or 1/second, which is equivalent to hertz. Okay, and the period is basically the time required to complete that one revolution. And the relationship between frequency and the period is T equals to 1/frequency. Okay, and because we talk about something that moving in a circle, definitely we need to find the relationship between the period and also the velocity. And as you know that the velocity is basically change of position divided by the change of time. Okay, so you can, if you put it as an instantaneous velocity, is going to be L over T. So Okay, so the relationship between L and T, like I mentioned before, theta equals to L over R. So theta, because it's moving in one circular motion, one circle is going to be 2 pi 360 degree L over R. So you're going to get L 2 pi R. So you're going to put it inside this formula. You are going to have it as a 2 pi R over T, and we are going to use capital T to represent period for one circular motion. Okay, so we are going to use all this formula that I already showed to you to find the centripetal acceleration or radial acceleration. Okay, let's apply the formula that I already mentioned before. Okay, so now the question asks you to determine the speed in meter per second at which the outer edge of the wheel is moving. So the question already gave it to you. The radius R, which is 0.29 meter, and being rotated at 830 revolution per minute. So this 830 revolution per minute represent frequency. So we are going to find in revolution per second. So 830 revolution per minute. So you know that 1 minute equivalent to 300, you're going to equivalent to 60 seconds. So you are going to get this one as a 830 divided by 60, 13.83 second. Okay, and then we already find this frequency. So for us to find the speed, definitely we need to find time, which is period, which is 1 over frequency. So you are going to get 0.072 second. Okay, so the relationship between period and also speed going to be the formula of V equals to 2 pi R over T. So 2 pi R is 0.29 meter and T is 0.072. So you are going to get 2 pi times 0.29 divided by the time, then you are going to get 25.2 meter per second. Okay, that's how you do it. Okay, very simple, right? Okay, let's move on to the next one. Okay. So I already showed it to you. So this is basically the proper way for you to write it. Okay, so this one I already mentioned that the theta can be called as the angular displacement. And the formula for the theta is S over R or L over R, and I already show you how to get this one. Okay, this one can be further discussed in chapter rotational motion. For this part is only a very basic angular displacement. Only we can use only basic formula. Okay, so let's move to the next question. Okay, so you have this one where there's a 150-gram ball at the end of the string is revolving uniformly in a horizontal circle of radius 0.60 meter. So we can actually say that this is basically a radius. The balls make 2 revolutions in a second, which is this one going to be frequency. Okay, so what is its centripetal acceleration? We know that when it comes to the centripetal acceleration, the formula going to be AC equals to V squared over R. So for us to find the V, we are going to use V equals to 2 pi R over T. Okay, so from the frequency is 2 revolution per second, which means that for us to find time or period is going to be 1 over 2. Okay, so 1 over 2, you are going to get 0.5 second. Okay, first we are going to find V. So V will be 2 pi, radius is 0.6 divided by the 0.5. So you are going to get 2 pi times 0.6 divided by 0.5. So we're going to get 7.54 meter per second. Okay, next we find the centripetal acceleration. So the AC going to be V squared over R. So 7.54 square divided by the R is 0.6. You are going to get 94.7 meter per second square. Okay, understand? Okay, good. Let's move on to the next one. Okay, so this is another exercise which is practically very easy. Okay, this one is the question asks you to find the acceleration also, which is basically the question asks you to find the centripetal acceleration. But now we need to find first period in second, so 27.3 days. Okay, so for you to find the second is going to be t equals to 27.3 days. So days is going to be t, so times 1 day going to be 24 hour, times 1 hour going to be 3600 seconds. So you are going to get this one is 2.36 power of 6 second. Okay, so the question already give you radius 384,000 kilometers, so we need to change that into radius. So for that we are going to get, that one is going to be 3.84 times 8 meter. Okay, this one going to be 3.84 times 8 meter. So the question asks you to find the acceleration. So a c equals to v square over r. So v square, the v square over r, so v, okay, v square over r, so we need to find the v first, which is 2 pi 3.84 times power of 8 over t, which is 2.36 power of 6. So you're going to get 2 pi times 3.84 power of 8 divided by 2.36 power of 6 is going to be a 1.02 power of 3 meter per second. So the question asks you to find the centripetal acceleration. Therefore, we are going to put it inside the formula of AC equals to V square over R. So you're going to get 1.02 power of 3 square over 3.84 power of 8. So square divide 3.84 power 8. So you're going to get 2.72 power of negative 3. 2.72 power of negative 3 meter per second square. Okay, so you got it? Okay, good. Okay, so very easy, right, for this one. Okay, let's move on to the next part. Okay, so when we talk about acceleration, okay, like I mentioned before in Newton's second law, you have an acceleration if you have force. Okay, so because force is the one that changed the magnitude and change the direction of acceleration. Now, when we talk about uniform circular motion, what happens is you are going to have the constant speed, but you change the direction. So the one that changed the direction is going to be force. So we're going to relate the Newton's second law with this centripetal acceleration, where we know that is going to be F equals to ma. So for us to find the centripetal acceleration is going to be m. A is v square over r, so mv square over r. Okay, and the direction of centripetal acceleration we will follow the direction of acceleration, which is always be toward the center. Okay, so basically here I just want to state that the centripetal acceleration is not new force, which means that centripetal acceleration is produced is because of other force. It can be tensional force or it can be frictional force. Okay, but it depends. Okay, it depends on the situation of the question. It can be other force also, but this force is the one that supply, or the force is the one that produce centripetal force. So when it comes to your FBD, your free body diagram, you cannot put any direction of centripetal force, because centripetal force is just to show that this force, tensional force or frictional force, is the one that produce centripetal force, which make this object moving in the center. Okay, so please take note that centripetal force is not a new force. It's basically produced by another force, which can be tensional force, it can be the frictional force, it can be Fn sine theta, And this force that I mentioned before is the one that produces centripetal force and to make sure that the object are moving to the center. Okay, so as you can see that in front of you, you have a diagram there. Okay, so you swing a ball in a circle on the end of the string. What happened is, if you want to swing it in a circle, you are going to pull the inwards, right? Inwards. Okay, so when you pull this thing inwards, what happened is this tensional force is the one that produce centripetal force. Okay, so because if you didn't have this inward force, what happened? It's not going to move in a circle. So when you apply tensional force, which means that you are going to produce a centripetal force to make sure that the ball are moving in the circle. So your tensional force is going to be the one that responsible to make sure that the object moving in the circle. But there's a one we call as a pseudoscience, which is the wrong facts about science. There's a centrifugal force. Okay, what happened here is centrifugal force doesn't exist. Centrifugal force doesn't exist. Okay, centrifugal force is basically the concept that there's some force that pulls this object outward. Okay, which means that this force is come from nowhere, and you feel that when you swing the ball in a circle, you can actually feel that there's something that pulls this ball outward, right? So the pseudoscience state that this outward force we call as a centrifugal force, which means that the force that comes from nowhere, which is wrong. Okay, centrifugal force doesn't exist. The one that makes the ones that produce this outward force when you actually swing the ball is basically come from the one that you give it, which is the inward force. Okay, so example, okay, you pull the ball inward, okay, because you want to make sure that the ball is moving in the circular motion. So when you have a Newton's third law, every actions have a reaction with the same magnitude, different direction. So when you pull inwards the tensional force, so the ball going to produce an outward force with this different direction, same magnitude, different direction. So this one we call as the outward force, not a centrifugal force, which means that this outward force come from the inward force that you produce. Okay, so it's not from this outward force is not come from nowhere. It's basically based on Newton's first law. Every action have a reaction, and if the centrifugal force exists, supposedly, okay, if the centrifugal force exists, when you swing a ball and then when you release, it means that you didn't give any tensional force. What happened is the ball going to move outward like that, but it doesn't happen right like this. Okay, what really happened is when you didn't put any tensional force over there, when you didn't apply any force, the ball going to move in the directions of the velocity at the moment it was released, which is tangential to the circle. So it's going to move in that direction. Okay, so that's the reason why centrifugal force doesn't exist, and that's the reason why centrifugal force is basically a pseudoscience, which is science that basically wrong. Okay, understand? Okay, good. Okay, let's move forward to the next one. Okay, so this is conceptual example. An object on the guideline is in uniform circular motion. The object is symbolized by a dot, and at point O, it is released suddenly from its circular path. If the guideline is cut, which means that you didn't apply any tensional force over there, will the object move along OA or OP? Like I mentioned before, the centrifugal force doesn't exist. So the directions of the velocity going to be at the moment it was released. Therefore, the answer going to be OE. Yes. Okay. Which is tangential to the circle. Okay. So the explanation is already here. Okay. I already mention to you about this. Okay, so this one, is going to move at a constant speed along the straight line in the direction it had at the moment it was released. Okay, so now we are going for the questions. Okay, so the question asks you to estimate the force a person must exert on a string attached to the 0.150 kilogram ball to make the ball revolve in the horizontal circle of radius 0.6. The ball made 2 revolutions per second. Ignore the string mass. Okay, so the relationship between acceleration, centripetal acceleration, and centripetal force is going to be Fc equals to mv square over r. Okay, so for us to find the mv square, for us to find the centripetal acceleration or centripetal force, after that we definitely need to find the v first, which is v equals to 2 pi r over t. Okay, so the 2 pi r, 2 pi 0.6, and your t is 1 over 2, because the one that actually give it to you is the frequency. It's going to be 1 over 2. So you're going to get for this one is 2 pi 6 0.5. You're going to get 7.54 meter per seconds, and then you insert that into the formula. So you are going to get centripetal force is make sure that you double check the units, make sure the units all in SI unit, because it's much safe if you use it in the SI unit instead of other units. Okay, so 0.15 times 7.54 square divided by radius 0.6, okay, times 0.15 0.6. So you are going to get your answer is 14.2 Newton. So this is the force that needs to make sure that the ball can actually moving in a circle. Okay, so another thing is that I need to show it to you is how to come up with the equation. Okay, so you need to look at the situation of the question. So, and then please take note, you cannot draw the centripetal force in your diagram, because centripetal force is not a force. It's basically just to show that this object moving in a circle. So the one that responsible for the centripetal force can be tensional force, it can be frictional force, it can be normal force, okay, or any other force. Okay, so example, if we have an object like that, okay, an example, this person head is downward like that, okay, and then this person the head is actually at the top like that. So what happens is we are going to come up with the equation. So this is the surface of the person sitting there. So basically what happens is normal force always be perpendicular, therefore your normal force going to be in that direction, and your gravitational force always be downward no matter what happens. So that's the reason why you're going to get Fg in that direction. Okay, so for us to relate with the centripetal force is going to be using this concept of Newton's second law, which is F equals to ma. So the equation is going to be Fn. Okay, I'm going to because the centripetal force is toward the center, so it means that I'm going to follow the directions of centripetal force. That's why I'm going to put it as a positive over there. So Fn plus Fg equals to what? Ma. So this A going to be Fn equals to, is going to be Fn plus Fg equals to mv square over r, like that. Okay, so for this one, the second person, okay, the surface is at the bottom, so the normal force is always be perpendicular to the surface. So it means that your normal force going to be like that. Okay, normal force is the contact force, so it means that the surface acting on the person upward. Okay, so what is about mg? Mg always be downward, okay, like that. So you're going to get Fn minus Fg equals to what? Mv square over r, and that's how you get the formula. Okay, what if this person, example, like in front of you, can actually say that this person, that this one, okay, what is the equations going to be? Okay, and okay, first thing first, you need to detect the directions of centripetal force, which is toward the center. Okay, so the normal force going to be in that direction, okay, and your mg going to be in that direction, which means that your Fn and mg is perpendicular to each other. So the one that going to supply, the one that going to produce centripetal force is going to be the normal force. That's why you're going to get Fn equals to mv squared over r. Okay, and same goes as this one. Okay, normal force in that direction, normal force in that direction. Okay, so it's basically toward the center, which is in the same directions as centripetal force. So that's why you're going to get the formula Fn equals to mv squared over r, and your mg is perpendicular with your normal force. Okay, but there are certain situations of the question that ask you the minimum speed, and the mostly that one is going to be asked at the top of this one. Okay, the minimum speed required to make sure that the object can move in the circular motion. So when the question state minimum speed, it means that the object didn't attach, or not really attached to the surface. So therefore we need to find the speed, the minimum speed is for the object to move in a circular motion, but means that the minimum speed here, the Fn going to be 0. Okay, there are certain questions where the question asks you when you swing the ball. So at the top of the circular motions, the question asks you to find the minimum speed. So means that at a particular time, the minimum speed you need to put at the tensional force as 0. So for this one example, if the question state minimum speed, what you need to do here is the formula at the top going to be this one. Okay, we are going to get from this one, which is Fn, it's going to be Fn plus Fg equals to mv squared over r. Okay, but when the question state minimum speed, which is the minimum value, therefore you need to put your normal force as 0, as if the object didn't touch the surface. Okay, so this one I already mentioned to you, and this is the equation that I mentioned for the minimum speed, where you can say that as if you didn't touch the surface, your normal force going to be 0, and that's how you get the formula for minimum speed. Okay, so make sure that you know how to derive the formula, and then please take note of the situation of the question. Okay, and it can be like this, or it can be like the next one I'm going to show you later. Okay, for this one, the situation is quite different. Okay, therefore we are going to draw the FBD first, the free body diagram first, before we proceed with the equation. So this one, for the top one, so there's a normal surface, or we can actually say that there's a contact with the seat over there. So therefore our normal force definitely going to be, yes, very good, is going to be upward, and your mg always be downward. So and your centripetal force always toward the center, which means that the one that going to follow the direction of centripetal force going to be the gravitational force. So I'm going to put the Fg as a positive. Fg minus Fn equals to what? mv squared over r. Okay, and the bottom one, okay, so your normal force in that direction, okay, same as the top one, and your mg always be downward. Okay, and this one, the one that going to follow the directions of centripetal force, going to be the normal force. So it's going to give you Fn minus Fg equals to mv squared over r. Okay, so please double check first the direction of force. Okay, and please take note that don't please do not include any centripetal force in your equation, because centripetal force doesn't exist. It just want to show you the direction of the movement of the object in the center, and the one that's going to supply, or we can actually say that the one that's going to produce the centripetal force, going to be either normal force, tensional force, or frictional force. Okay, so for this one, the questions already show you how to draw the FBD, but please make sure that you draw it by yourself. The situation of this one, the question asks you to determine the minimum speed the ball must have at the top of the arc so that the ball continues moving in a circle. So at the top of the arc, what happens is, this is going to be your tensional force, and your mg going to be in the same direction. So your tensional force and mg will be in the same direction with your centripetal force. So the equation is going to be ft plus mg equals to mv squared over r. But the question asks you to find the minimum speed. So like I mentioned before, when it comes to the minimum speed, it means that your tensional force is going to be 0. So this one going to be 0. So right now mass can be cancelled out. So you are going to get your formula for the V is Rg square root everything. So so your 1.1 meter long cord going to be the length of this cord, which is 1.10. So you just put it 1.10 times 9.81 square root everything. So you're going to get 3.283 meter per second. And the next question asks you to calculate the tension in the cord at the bottom of the arc, assuming the ball is moving at twice the speed of the cord, of the part A. So the first thing that we need to do is we need to come up with the equation first. So at the bottom, we are going to have Ft. Tensional force always be outward from the body. Mg always be downward, and the one that follow the directions of centripetal force going to be tensional force. So the equation is going to be Ft minus Mg equals to Mv squared over R. So your Ft will be Mg plus V squared over R. So M 0.150, 9.81. Plus with the speed, which is the question state twice the speed. So it becomes 2 times 3.283 square divided by the tensional force over there. So it's going to be 1.10. Therefore you are going to get 7.35 Newton. So that's how you do it. Make sure that you come up with the equation first, and then substitute the number, and then you are going to find the answer. Make sure that you draw the FBD first, the free body diagram. So let's proceed to the next one. So one of the applications of the uniform circular motion is going to be conical pendulum. So when it comes to the conical pendulum, definitely you need to draw it first. It's totally different from the previous one. So I'm going to show you how to draw the FBD for this part. So example, you have this one ball revolve or moving in circular motion. So this one attached to this one. And the angle going to be that direction. So the first thing that you need to do is you need to resolve the component of the Ft there. So this is going to be your Ft, which means that this one going to be your Ft cos theta, because your angle touch what is this, and this one going to be your Ft sin theta. Another force that you need to draw is going to be mg, gravitational force. And please do not draw the centripetal force. You know that the centripetal force will be in the same direction as the Ft sin theta. Okay, so we need to separate into two components, which is x component and y component. So I'm going to show you the y component first. Okay, so the y component going to be ft cos theta minus with the mg equal to 0 because it doesn't move upward. Okay, so you're going to get your ft is mg over cos theta. Okay, next I'm going to show you the x component. Okay, so the x component going to be ft sine theta equals to the mv square over r. Okay, so the next part is you are going to put your ft here into these equations. So you are going to get mg over cos theta sine theta equals to mv square over r. So you can cancel the m. So sine over cos is tangent theta. So we are going to get tangent theta g tangent theta v square over r. So for you to find the angle is going to be tangent theta v square over rg. Okay, so that's how you come up with the equations for the conical pendulum. Double check first the angle there, okay, and then please resolve the components and separate that into y and x, and then you combine by putting the ft, okay, and then you are going to get the final equation. Okay, so this one, okay, so we are going to try to answer these questions using the formula that we find it before. Okay, so the question asks us to find the tension in string, speed of the ball, and the centripetal force. Okay, so before that we need to find the r here. So using the concept of tangent, sine, and cos, so they already give you 30 degree and the length is 1.2. So your r going to be sine theta opposite over hypotenuse, so it's going to be r over 1.2. So you're going to get r is 1.2 sine 30. Okay, so you're going to get that is 1.2 sine 30 is going to be 0.6 meter. Okay, so the next one is you need to draw the FBD first. Okay, the FBD first. Okay, so you have like this object. So this is going to be a potential force. So this is going to be ft sine theta. I'm going to use the angle that touch y-axis, which is 30 degree. You can actually use the 60, but you are going to change the sine and cos. So ft cos theta, definitely you are going to have mg, and you don't have to draw the centripetal force, but you know that the centripetal force will be in the same direction as the ft sine theta. So the one that is responsible to make sure the object is moving in the circle is going to be ft sine theta. So the question asks you to find the tensional force over there. Therefore, I'm going to use the formula, which is ft cos theta minus mg equals to 0. So ft is basically mg over cos theta. So m is 0.15 times 9.81 over cos 30. So you are going to get that one is 0.15 times 9.81 divided by cos 30. So you are going to get 1.70 Newton. Okay, you can actually use that the s component for you to find the tensional force. It's up to you. You are going to get the same answer. Okay, then another question asks you to find the speed of the ball. Okay, so for you to find the speed of the ball, definitely you need to come up with the what we call as the s component, which means that your s component now going to be ft sine theta equals to mv square over r. So for you to find the speed is going to be r ft sine theta over m square root everything. So r is 0.6 times tensional force sine 30. Okay, and then divided by m is 0.150. So you are going to get 0.6 times 1.70 sine 30 by 0.150. So we're going to get 1.84 meter per second. Okay, and the question asks you to find the centripetal force. So you know that centripetal force is mv square over r. So m is 0.15, v is 1.84 square, divide by the r 0.6. You are going to get 0 times 1.84 square divided by 0.6. So the answer is going to be 0.846 Newton. Okay, so that's how you do it. Okay, so definitely please make sure that you draw the FBD first and then come up with the questions, and it's going to be easy if you do like that. Okay. Okay, so let's move forward with the next application. Okay, the band track and an unband track. Okay, so basically what happened here is when it comes to this uniform circular motion, the one that you can actually see that when you want to move in roundabout. Okay, so when you move in circular motion, definitely you are going have some force that makes sure that you move in circular motion. So example like this one, the one that force you to move in the circular motion is going to be the door. Okay, the door apply force to you, and at the same time the seat, okay, the frictional force from the seat also apply force toward the center to make sure that you move in the straight line. If there's no force from the door and from the seat, what happen is you are going to move in a straight line. Okay, so when it comes to the band track, okay, so you need to understand that the one that produce centripetal force definitely going to be frictional force. So example, if you want to move like that, so you have car like that, so you know that your centripetal force in that direction. Okay, I'm not going to draw it inside the FBD just to show you the centripetal force is toward the center, but the one that going to produce a centripetal force is going to be frictional force. Okay, so the frictional force is going to be in that direction. Okay, and then is going to have a normal force come from the surface of the road, and then you have a mg. Okay, so when it comes to this, the one that will be equal to the centripetal force is going to be FFR equals to mv square over r. So as we know that we have two types of frictional force, it can be static frictional force or kinetic frictional force. But to make sure that you still stick to the road, still on the road and not skidding, definitely the one that going to be responsible is static frictional force. So means that your static frictional force should be large enough to make sure that you stick to the road. But what happen if your static frictional force is not enough, you are going to skidding, and then accident going to occur. Okay, so that's why static frictional force is the one that responsible for this. Okay, so when it comes to the frictional force, definitely you know that the formula going to be FFR equals to mu s Fn. So from this picture, your Fn going to be mu s mg. Okay, so this is for the unbent track, which is the flat surface. Okay, so you can see that from the picture, there's a path over there. So there's some path that basically can actually move in the circle or move in the curve, which means that the static frictional force enough to make sure that it can move in the circle. But you can see that there's some of the path basically shows that the frictional force or static frictional force is not enough. It means that it's going to be skidding. Okay, means that it cannot move in the circular motion. Okay, so therefore, if the question asks you whether the car can actually move in a circle or not, definitely you need to find the FFR, which is static frictional force first, and then you need to compare it with the centripetal force, which is mv square over r. If your FFR is larger than your centripetal force, what happen is it's going to move in a circular motion. But if your FC is larger than your FFR, then it's going to be skidding. Means that it's not going to move in a circular motion. That is for flat surface. Okay, this one already mentioned it before, so you can actually read this. Okay, so the one that responsible for the frictional force is going to be static frictional force, because as we know that static is larger than your kinetic frictional force. Okay, so for this kind of questions, okay, which is in front of you, okay, definitely you need to draw the FBD. Okay, so the FBD is for this one is already draw it for you, but in the exam questions, definitely you need to draw it by yourself. Okay, so the question asks you to find whether the car follow the curve or will it skid. Okay, so like I mentioned before, you need to compare between frictional force and also centripetal force. So we find the centripetal force first, and then we compare with the frictional force. Okay, so centripetal force, as we know that the formula going to be Fc equals to mv square over r. Okay, so it's going to be Fc equals to mv square over r. Okay, so your m going to be 1000, your v square going to be 15 square. Okay, and your r going to be 50 meter. So this one, 15 square times 1000 divided by 50, so you're going to get 4500 Newton, which means that for the car to follow the curve, they need at least 4500 Newton. Okay, so now we find the frictional force, whether it's enough or not. So we know that the formula for frictional force is going to be FFR equals to mu s Fn, and because this is the flat surface, so your mu s going to be Fn equals to mg. So your mu s is going to be 0.60, m is 1000, and g is 9.81. So you are going to get 0.6 times 1000 times 9.81, and the answer is 5886 Newton, which means that this value is larger enough than your centripetal force, which means that for question A, the car follow the curve. That's how you solve the questions. Okay, because the static frictional force is larger than your centripetal force, definitely is going to follow the curve. Okay, what about question B? When it comes to the question B, okay, we are going to find the frictional force. So the pavement is IC and mu s is 0.25. Okay, so FFR equals to mu s mg. Okay, so FFR going to be 0.25 times 1000 times 9.81. Okay, so you're going to get 0.25 times 1000 times 9.81. The answer is 2453 Newton. And you can see that from this answer, the question B, the static frictional force is not enough because it's lower than the centripetal force. Therefore, for question B, the car will skidding. Okay, so that's how you solve the questions for if the question asks you to find the whether it's follow the curve or it will skid. Okay. Okay, next we are going to talk about bank track. Okay, so basically what happened here is, okay, for the flat curve, the one that responsible for your centripetal force going to be the frictional force. Okay, when it comes to the bank track, the one that create or build the bank track, they are going to build without friction. Okay, they are going to build the bank track without friction. And it means that we are going to have one speed which we call as a design speed. So if your design speed, if the question state design speed, design the bank track with this speed, it means that the bank track doesn't need any friction. Okay, so which force that responsible to produce a centripetal force. Okay, so we are going to draw the inclined plane first, but there are some slightly changes to the Newton's law RBD that we draw it before. Okay, so example, if we have one inclined plane, okay, and then I put it box, this box is as if this is a car. Okay, so definitely your normal force always be perpendicular to the surface. Okay, and then you are going to have mg here. Okay, so before this, in Newton's law, we are going to resolve mg, which means that we are going to have mg sin theta and mg cos theta. But for this one, to make it easier for your calculations, it's better that you resolve normal force. It's because of your centripetal force didn't follow the path of the inclined plane. It's going to be towards the center. Okay, so to make sure that it's easier for you to find the centripetal force, which is horizontally to the center, it's better that you resolve normal force instead of mg. You can actually resolve mg, but you are going to find FC centripetal force in x component. You need to find the centripetal force in y component. Then you need to find the magnitude, which is the equation is going to be longer. So to make it easier for you guys, please make sure that your y component going to be straight, which is vertically, and this is going to be your s. Okay, so the one that we are going to resolve here is going to be your normal force. So the angle always be given, which is horizontally touch the x component. So your angle for this one going to be, example, okay, if your angle is 20 degree, okay, you know that zigzag, this one going to be 20 degree also. Okay, so this one going to be, okay, this one going to be 90 minus 20, so therefore the 20 is going to be in that direction. So this one going to be what? Fn cos theta. So this one going to be Fn sin theta, if I'm going to use the angle that given, which is the angle of the inclined plane. Okay, so the one that responsible to produce a centripetal force definitely is Fn sin theta. Please take note, when the question state design speed or the inclined plane is designed, definitely there will be no friction. Okay, definitely there will be no friction. So the equation for the x component going to be what? Is going to be Fn sin theta equals to mv squared over r. So the one that is responsible to produce a centripetal force to make sure that the car move in a curve, definitely going to be Fn sin theta. Okay, and for the y component, the equation is going to be Fn cos theta minus mg equals to 0 because it doesn't move upward. Therefore, your Fn cos theta equals to mg. Okay, this one, if the Fn sin theta enough to give you centripetal force. What if your Fn sin theta not enough? So the one that going to be helper is going to be frictional force. Okay, please take note, when the question state design this inclined plane, please do not put any friction. But if the question state that if there's a friction, okay, or maybe we can actually say that if Fn sin theta is not enough, so what force going to add up to make sure that it's moved in a curve? Definitely is going to be frictional force. And what frictional force going to be? Static frictional force. Okay, so I'm going to show it to you how to draw the FBD if, example, the Fn sin theta is not enough. It means that the speed that you drive, okay, example, if you drive the car with speed more than design speed, okay, if you drive the car speed more than design speed, so what happen is you are going to tend to skid, whether it's going to be inward or you are going to skid upward. Okay, at that moment definitely you need to have a FFR. Okay, if you drive the car with speed larger than your design speed, what happen is definitely you need to have a FFR, static frictional force, to make sure that you stay at that track. You're going to follow the curve. Okay. So I'm going to give it the example. If you drive with speed larger than your design speed, so there are two possibilities, whether you are going to move inward or you're going to move upward. Okay, so it's going to be, okay, I folded this. Okay, example, okay, if you drive a car larger than your design speed. Okay, so mg, okay, remember we are going to resolve fn, no mg. Okay, fn sine theta, this one going to be fn cos theta if I'm using angle here. Okay, so if your speed, your drive speed larger than your design speed, definitely you need to have a frictional force. Okay, example for this one, if you move inward, definitely you need to have something that oppose the motion inward, which is definitely your frictional force. So your frictional force going to be parallel to the surface, so you need to draw it like that. Yes. Okay, so the equation is going to be a little bit different, where you need to resolve the FFR, because FFR right now follow the path of the inclined plane, so therefore you are going to have FFR in x component, which means that the angle going to be okay, if I'm using the same angle, the angle going to be here. Okay, so this one going to be FFR cos theta, so the y component going to be FFR sin theta. Okay, so the equation is going to be quite long, okay, but you can do it slowly. Okay, definitely you are going to get the right equations of it. Okay, so for the y component, this is example if you move inward. Okay, if you move inward, okay, you tend to skid inward. Okay, y component going to be fn cos theta plus ffr sin theta minus mg equal to 0, because it doesn't move upward. Okay, and your x component here going to be fn sin theta. Like I mentioned before, any force that follow the directions of centripetal force, you make it as a positive because it's much safe and you avoid careless mistake. So it's going to be fn sin theta minus ffr cos theta equals to what? Mv square over r. Okay, that is if you skid inward. What if you skid outward? Okay, so the same diagram, you have fn, you have mg, you have fn sin theta, you have fn cos theta. So I'm going to use the angle here. Okay, so if you move outward, you tend to skid outward. Okay, you tend to skid outward, so definitely you need to have something that oppose the motion outward, which is definitely going to be frictional force. This one if you drive with the speed more than design speed, so your frictional force is going to be in that direction. Therefore when I resolve, I'm going to get FFR sin theta, because my angle going to be here, and another one going to be FFR cos theta. Okay, so the equation for this one, for the y component, is going to be fn cos theta minus ffr sin theta minus mg equals to 0, because it doesn't move upward. And then you have the x component here, which means that the fn sin theta plus ffr cos theta equals to what? Mv square over r. Okay, this is the example if you need a friction, but please make sure that you read the question carefully. If the question state design this band trap, definitely you don't have to put the friction. But example, if the question state that your speed is more than your design speed, then definitely you need to have a friction in your FBD. But please take note, for you to find the angle, you need to make sure that the equation is without frictional force, because you designed the bend track without frictional force. So please make sure that you use the normal formula, which is Fn sine theta equals to mv squared over r without frictional force. Okay, because the design speed, or you design the bend track. Or maybe if the question asks you to find the angle of the inclined plane. By example, if the inclined plane, if the Fn sine theta is not enough, definitely you need to have a friction, yes. Okay, and please take note, you need to resolve the frictional force. Okay, that's how you do it. Okay, so this is the questions. Okay, the last question in the slide. Okay, so for the car traveling with the speed around the curve of radius r, determine the formula for the angle at which road should be banked so that no friction is required. So means that this one you didn't have to draw the frictional force. Okay, so I'm going to draw it for you, even though the question already gave it to you. But please take note, in the exam, in your exam questions, there will be no diagram for FBD. Okay, you need to draw it by yourself, and definitely it's compulsory for you to draw the FBD. Okay, because it's much easier for you to come up with the question if you draw the FBD. So it's going to be mg here, so it's going to be Fn it's going to be Fn sine theta. Okay, sorry, I think this one. And then you have a Fn cos theta. Okay, because I'm going to use angle here. Okay, so the equation is going to be, the question asks you to find the theta, right? Determine the formula for the angle. So it's going to be Fn cos theta minus mg equals to 0. This is for the y component. So you put Fn as your subject, which is Fn equals to mg cos theta. And then you come up with the x component, which is going to be Fn sine theta equals to mv squared over r. So just put this Fn, substitute into this one. So you are going to get mg over cos theta sine theta equals to mv squared over r. So mass can be cancelled here. So you are going to get your tangent theta is v squared over rg. Okay, familiar, right? The equations, it seems like a conical pendulum. Okay, but the difference is the conical pendulum you have a tensional force, but this one you have a normal force. Okay, so the question asks you B, what is the angle for the expressway of ramp curve of radius 50 meter at the design speed of 50 km per hour? Okay, so please make sure that you change first 50 km per hour to meter per second. Double check the unit first. So for B, 50 km per hour, so it's going to be 1 kilometer equivalent to 1000 meter times 1 hour is 3600 seconds. So you are going to get 13.9 meter per second. Okay, so the question asks you to find the angle. Therefore, we are going to use the formula that we derived before, which is this one. So you are going to have tangent theta equals to v squared is 13.9 square over r is 50 meter. Okay, 50 meter, and your g is 9.81. So you are going to get 13.9 square divided by 50 times 9.81. So you are going to get tangent theta. The angle is 21.5 degree. Okay, so that's how you solve the problems. Okay, therefore definitely please make sure that practice a lot when it comes to the come up with the equations. Okay, so to derive the equation, it depends on the marks given in the question. If the question just like 2 marks, you can just directly use the formula. By example, if the question like 5 marks, definitely you need to derive it first up until you get the formula, and then substitute, and then you get the final answer. Okay, Okay, I think that's all for now. Okay, so hopefully you understand the uniform circular motion and how to come up with the equations, okay, and the applications of the uniform circular motion in conical pendulum and the bank track. Okay, so if you didn't understand, please ask. Okay, and I'm going to see you for the next chapter. Okay, so thank you very much. Assalamualaikum and goodbye.